Hello, in this video we're going to look at electric current, what it is, how we measure it, what it does. So firstly, what do we mean by current? Well, it's helpful to think about an analogy. If we think about a current flowing in a river, then you can imagine what that means. If you've got lots of water going past very quickly, then it's a strong current, and if the water is just flowing past very gently, it's not a very big current. But there's this idea of something flowing. So a current is a flow of something. So a current can be treated a bit like the flow of water in a river. So if there's a current, an electric current must be the flow of something. And what is it that's flowing? Well, if we go back to our list of things, the thing that's flowing is actually electric charge. So in actual fact, electric current is the flow of electric charge, and the more charge that is flowing past in a second, the bigger the current. So that allows us to put a definition down for electric current. So current, it's the flow of charge, but as a definition, it's the rate of flow, and the rate of means how much per second. So we can give it two definitions. One is using the word rate of, and the other one is just per second. So we can talk about the current being the amount of charge flowing per second, or we can say it's the rate of flow of charge, because the rate of anything means how much per second. The rate of energy transfer is how much energy is transferred per second. So an electric current is the rate of flow of charge. We can't see the charge, we can't even see it flowing, but we can tell what's happening because we can see the effects. So if I draw a simple circuit with a battery and a light bulb, we can draw arrows on it to represent the current flowing around that circuit. If there's arrows, we have to have a direction, and we have to choose a direction. Well, because we can't see it, we could choose either direction because it doesn't really matter to us. But that's what happened a long time ago, and they had to guess which direction the current was flowing because they didn't know what was actually happening. So they guessed that the current flowed from plus to minus, because that seems to make sense. You go from somewhere where there's plus of something to where there's minus of something, and that's where it flows. In actual fact, what's happening is electrons are negative and they flow the opposite direction. But if you can keep that out of your head for most of the time and just imagine that there's something flowing, and we say that the flow is from the plus to the minus around the circuit. Okay, so we draw arrows. We can draw arrows on the diagram to show which way current flows. If they just ask current, that's the way it flows. So what does that tell us? Well, if we look at the current here, there's a flow all the way around. That means that if we have a certain current here, we've got the same current here with charges are flowing around here. They don't build up somewhere, and they don't leak out. So wherever they start from, they have to end up there in the end. That means that if we were to measure the amount of current at this point and measure the amount of the current at this point, it would be the same. There's nowhere else for the current to go, so the current is the same everywhere. And if I had something with two light bulbs, like this, then I can draw the same arrows to represent the current, and there's nowhere else for the current to go, so it must be the same all the way around. If I was to measure the current here and here and here, I should get the same value. Now that comes on to measuring the current. If I actually want to measure this current, it's in the circuit, it's in the wire. I have to put something in the way of the wire to measure that. So I have to break the circuit and put the ammeter in its place, in the place of a gap, to actually be able to measure the electric current. So say I wanted to do this one and I wanted to measure the electric current here, I have to make a gap in the circuit and I put my ammeter connected there like that. So that would measure the current flowing through there. If I wanted to put it here, I'd have to make a gap here and put the ammeter in the gap. So let's measure this one and just prove for this case that the current is the same on both sides of the battery. So let's make up a circuit first. So here's my light bulb, and I want to put the ammeter into the circuit both sides of the light bulb. So I want to break the circuit here, and I want to break the circuit here, and I want to measure the current. So let's break the circuit this side first, and I need to replace that with my ammeter. So my ammeter is here. I need to put that in the way where the gap was, and we measure what the current is. And we get a current of 0.36 amps. Okay, so 0.36 amps if I break the circuit there. Let's reconnect. Now I'm going to move the ammeter to the other side of the circuit, and I'll measure it there as well. Okay, so I reconnect my ammeter in the other side of the circuit, and I'm getting, can you read that? Yes, 0.36 amps again. So whichever side of the light bulb I connect to the ammeter, I get the same current as we predicted just by drawing on the diagram. Now let's try the other circuit with the two light bulbs, one after the other, which is two light bulbs in series. So I'll set up the circuit first. Okay, so there's my series circuit set up, two light bulbs, one after the other. It goes from the plus of the battery, so this is this circuit, it's just that my battery's up the other way. Plus of the battery goes to the first light bulb, to the second light bulb, and back to the minus of the battery. Now, we've predicted that the current should be the same all the way through. It's different light bulbs, so it might be a different current. So let's measure it first at this point, then I'm going to measure it at that point, and then I measure it at that point. Okay, first point, I have to connect it in here. Okay, so I've connected it at my first point and I get 1.30 amps. Now I'm going to connect it in the middle here. So I'm going to take my ammeter out of here. Oh, it's gone down to 1.29. Connect it into here. So my ammeter is now connected in between the two light bulbs, and 1.3 amps, 1.29 amps, just the same as it was before. And finally I want to connect my ammeter into here and see what we get. Okay, let's connect it into here. And we have our ammeter connected in the final position just before the negative of the battery, and I get 1.3, 1.29 amps again. So wherever I measure the current in that circuit, it's exactly the same. So that was a series circuit, but when I was looking at circuit diagrams before, we talked about a parallel arrangement, and we had this kind of arrangement. So our battery connected to two light bulbs, one here and one here. Now let's look at where the current is going to flow, or how the current can flow, because there's now two alternatives. So I'm going to draw the current in different colours now. So let's imagine the current is flowing through this first light bulb. Okay, so we've got current charges moving around through that first light bulb, and they come back to the battery. But for the other light bulb, we need some current there as well. So let's draw the current going through this light bulb. It's going to join up with this current here, flow back around and out this way. So you can see that we've got two different ways that the current can go, and some of the current goes down one way, some of the current goes down the other way. But what comes from the battery splits up into two parts. It may or may not be equal parts. In fact, I'll set up a circuit so that they're probably not equal parts. If the two light bulbs were identical, then these two currents would probably be identical, but they don't have to be. And if we measured the current here at this point, so just after the battery, then it should split up in the two different parts, which add up to the current from the battery. So let's try that out and see if that is what we actually get. And I might have to take a note of the current so that we can add them up as well. So here's my parallel circuit. Both my light bulbs are connected to the battery in the same arrangement. If I connect from the positive, I can go through one light bulb and I can go through the other light bulb. Okay, in the same way I can say going through one light bulb and go through the other light bulb. I can measure the two currents. I can measure the current through each light bulb at this point and at that point. So let's measure those first. So let's look at the large light bulb. Let's take the circuit apart. I'll measure the large light bulb current. Okay, and that is 1.80 amps. So large was it's gone down to 1.79 now. 1.79 amps, and small, let's measure the small light bulb. So I have to disconnect this. Okay, so this is now going to be measuring the small light bulb, which is giving me 0.35 amps. So 0.35 for the small light bulb. So the final thing I have to do is measure the current coming directly from the battery, which is this current here. Okay, and the easiest way to do that is to disconnect both the light bulbs at once from the battery and connect my ammeter in the gap there. So let's do that. So my ammeter is now connected in the gap and I get 2.15, 2.14 amps. Okay, it was 2.15, 2.14, 2.14 now. Okay, so let's disconnect that so I can see what I'm doing because it's a bit bright. So that was 2.14 amps together, so both. Right, let's add up these two and see what we get. So 1.79 plus 0.35 equals 2.14. So as if by magic, our prediction has worked. If I measure the current through here, it was 0.35 amps. This one was 1.79 amps, and here it was 2.14 amps. These two add up to be the same as that one. And that's a general rule with any time current is coming to a junction. It will split up, not necessarily equally. Okay, these are not the same current, but it will split up into two parts which add up to the same as what was coming in. So what goes in must come out. If I did the same at this side, what would happen is these two currents would then add up again to give 2.14 again here. Okay, it'd be 1.79 at this point, 0.35 at that point. So it's a general rule. Current in a parallel circuit, the current will split up at a junction and go two different ways, but the total current coming out will be the same as the current coming in. And in a series circuit like this, where there's only one way and there are no junctions, you can tell there's no junctions because there's no black dots. If there's no junctions, the current is going to stay the same wherever you are in the circuit. So that's our general rules. Now the final thing is to put some equations. So we had our definition as the rate of flow of charge. We've got our things that we can measure, and we just need to put an equation down for current. So current, electric current, measured in amps, it's the amount of charge flowing per second. Amount of charge per second, per means divided by, so we can work out that that is charge divided by time. It's the charge flowing, which is in coulombs, divided by the time in seconds. So to put that as an equation with symbols, we use the labels for the thing. So we have I for current equals Q for charge divided by t for time. And as a triangle, to make anything like that into a triangle, if there's a fraction, the thing that's on top of the fraction goes at the top of the triangle, and the other two things go at the bottom. So I times t goes on the bottom. So now if I wanted to find the charge, I could put my finger over the Q and I get I times t. Current times time would give me the charge. If I want to find the time, charge divided by current. If I want to find the current, charge divided by time. So that's our equation for electric current. So that's our first of the equations.